Good day. My name is Stefan Boodoo, and I will be presenting for the ICON eTech 2020 conference. And the title of my presentation is Developing Parallel Computing Algorithms Using GPUs to Determine Oil and Gas Reserves Present in the Upstream or the Exploration Sector. This is done by myself and under the supervision of Dr. Ajay Joshi. He is my supervisor. And to start off with my project, the two major objectives of my project are to perform an in-depth study on parallel programming methodologies, models, and techniques. And I chose to focus on the GPU computing model, which made use of Nvidia's CUDA architecture and programming model. And the second major objective would be to perform a study and analysis on hydrocarbon exploration methodologies. And I chose to focus on well logging. So Objective 3 and 4 is based on Objective 1 and 2. And Objective 3 is to acquire datasets and data parameters that are to be used in my project, and this data must be cleaned, analyzed, and extracted from its proprietary format into a format that can be manipulated and used. And then relevant parameters and equations are then modeled, and you're going to use this raw data and take the raw data and really put it into parallel algorithms and to get a result of the experiment of the project. And this result can either be oil, gas, water, or shale rock. So basically what happens is you use the knowledge of well logging and of GPU computing, and you're really trying to find where oil and gas reserves may be, but through methods of using computations of parallel processing or supercomputing. So an introduction into my project would be really introducing high-performance computing. And high-performance computing is really essentially the ability to compute complex calculations and process vast amounts of data and as quickly and efficiently as possible. So this type of computing is a computing that is highly parallel in nature, as in contrast to typical processing, which is more sequentially done. And because this is done on parallel hardware, right, it will employ the use of parallel software using parallel algorithms and techniques, right? And what all this talk of parallel simply means is parallel computing aims to utilize multiple computational units or multiple units that will use to calculate something or give a result. And it will use these computational units to solve a problem by taking this problem at hand and breaking it up into small parts to be solved concurrently to arrive to a solution. So really using big amounts of data, big amounts of anything here to arrive at a solution as quickly and efficiently as possible through this method of breaking up the computation itself on multiple computational units. And the way in which this is done, and I am doing it, is through GPU computing, right? So what GPU computing really does, it takes smaller and more efficient cores as opposed to like a regular CPU, which is, highly specialized and much more bigger. This uses much smaller and more efficient cores, which is the foundation of a massively parallel architecture, and performs the computations there. And the GPU is the hardware aspect of everything. The software aspect, the GPU makes use of, in this case, what I'm using is Nvidia software, or Nvidia's computing platform, which is CUDA. That's the Compute Unified Device Architecture. So what this really is just a parallel programming model that makes use of instruction set from Nvidia to solve large data-heavy computational problems. The way in which this is done, or the program is executed, as you can see from the diagram as well, you'll take the relevant data at hand, you'll carry it from the CPU memory to the GPU memory, and the GPU memory is really where everything is being done. And this data is loaded onto the GPU memory and is executed or is acted upon. So this is where your software and your algorithms and whatnot will act upon the data and produce the result. And then this result from the GPU is copied back to the CPU memory, so you could actually see, okay, this is what went on, this is what happened here. And the way in which this is done on the GPU is through a method of grids, blocks, and threads. So as we can see in the diagram here, right, what really happens is the software CUDA, really, its instruction set executes a large number of threads to exploit parallelism, and each thread is applicable to a computation. And then these threads itself are further grouped into blocks. And then these blocks are further grouped back into grids here. And what a grid is really just a set of thread blocks that will allow for independent execution. So that was really how the computation is done on the GPU side. That's the real mathematical basis behind it. So the logic that is fueling the math comes from the well logging or the petroleum side. And what this is doing is well logging is a method used for recording rock and fluid properties to find an oil and gas containing zone, right? And is a tool that all people in the petroleum field utilize to determine if a reservoir produces oil or gas or hydrocarbons or any kind of hydrocarbon, or whether it doesn't produce at all. The way in which this is done, you use something called logs and log relationships. So we have 4 logs here, right? So for example, gamma would be used to determine, based on the values you're looking at, determine whether you're dealing with shale rock, you're dealing with sandstone rock, dolomite, or limestone. Density will provide the bulk density along the formation. Sonic logging will talk about the capacity to transmit seismic waves, so you know how you're dealing with that. Neutron and stuff will indicate whether it's an oil or water reservoir by measuring the hydrogen index. And then when you look at log relationships between neutron and density or resistivity, these again will further tell you or indicate whether you're dealing with oil, you're dealing with gas, you're dealing with water, and so on. So in the results, this is exactly what a well log looks like, uncleaned, unanalyzed, anything. This is just your raw data here. So you could see the values where we talked about just now with sandstone and resistivity and whatnot. And you see these just a mass of values here just existing. So this is just your raw data. So typically what people in the petro field or well loggers will do, they would make sense of this data and will plot into something like this. And each one of these curves would have to be analyzed in relation to one another independently to see, okay, we're dealing with gas here, we're dealing with rock here, we're dealing with oil, we're dealing with water, and so on, right? So it's a very lengthy and time-consuming process, right? Using GPU computing, since everything can be done much faster, this will load, for example, here, the same data and analyze the data into a result looking like this. So you can see on the columns, there's log depth, there's gamma, there's neutron, and these same raw values will be passed through the algorithm and through different equations and parameters and be modeled and examined, and it will produce something looking like this in the final scenario. So going downwards is depth-wise of our well. So as we're going down, you could see on the rightmost column, you could see the final results of the well in the F column, where there's shale at the certain depth, then some water, and then at the bottom of the well, you're seeing an indication of hydrocarbons. So what this is essentially doing is performing the same calculations as you would see in the well log example here, but instead of doing it line by line or area by area, this can handle this computation to perform it instantaneously in a couple of seconds, giving you in the field, you know, as an aid, as a second backup, like, okay, this is what it would look like. So you would know probably what areas to focus on looking for hydrocarbons and such. In conclusion, this is the end of my project here, and as you could see, all the objectives were met. We got the required knowledge and parallel processing, the data was cleaned and extracted, all algorithms were developed, and all the parameters were modeled, and lastly, we got the reservoir analyzed and modeled to show whether it was shale water, oil or gas reserves, and yep, that's it. These are the references, and well, in short, thank you for your time. Thank you for having me.
All right. Thank you very much to Stefan. I don't believe that Stefan is online, just to give him an opportunity to speak up if he is, but I'm not seeing him. So unfortunately, we will not be able to take questions for this presentation. However, if you have questions concerning this one, please do email the author, and the email address will be available in the abstracts. So